Hello, NPTEL office. Can you confirm you can hear me? Can you see if you can hear me? But voice? Yeah, hello, hello, hello. Okay, okay, great. Okay, thank you. Are we live NPTEL office on YouTube already?
Yes, sir, you are in live.
Okay. So I can see Pooja is already there. So should we ask her to go ahead and ask questions? Or should we wait till 4 o'clock? Pooja, if you're there, I've seen your questions, so I can answer it right now if you are online already. If you can confirm you can hear me, then I'll just go ahead and answer.
Yes, sir.
Huh. So I think the first question was with regards to the exam, right?
Yes, sir.
So in the exam, you can expect something similar to what is there on in the assignments. So there are multiple choice questions as well as numerical problems that you have to work out, and there's more of numerics. Square. So you'll be expected to work out problems in the exam. So yeah, so there are some theory questions, and but there's quite a there will be even you should expect numerical questions also. Okay.
Yes, sir.
Okay, so the other question I think was regarding Jeffrey's fluid.
Yes.
So two Jeffreys fluid is in parallel to each other. So I mean, I have something that is worked out right in front of me. Um, and you can check it for your correctness.
Yes.
So let's say you have one Jeffreys, which is E1, eta 1 in parallel, and then along with that, and I'm sorry, there will be some background noise because of some construction going on.
Okay.
So if you need me to repeat anything, I can do that.
Yeah. Okay.
So let's say E1 and eta 1 are in parallel with eta 2 as the first Jeffreys element. And then the second Jeffreys element is E2, eta 3 in parallel. And then the other one is eta 4. And these two are again in parallel to each other. So then if you apply a known amount of force, F, let's say, then the two will suffer a displacement. And in this case, the two displacements will be the same. Right? So both of them will experience a displacement of delta x. The force distribution will be, the forces will be distributed between the two. So if you say F1 is being experienced by one of them and the other is F2, then the net force F is equal to F1 plus F2. And then you go ahead and you have to write the individual constitutive equations for the Jeffreys fluids. So for the first one, and uh, I can maybe ask Sarath to even post it in your
exam. There is a portal for asking questions.
so he can even post this solution there, and you can also take a look. But what we do is for the first element, let's say you'll have the multipliers for the force will be eta 1 plus eta 2 plus d, d being the operator, plus E1. And on the other side, you will have eta 1, eta 2, d square plus eta 2 E1 d multiplied by delta x. And for the other one, you'll get eta 3 and eta 4 multiplied by d plus E2, the whole thing multiplied by f equal to this will be eta 3 into eta 4 d square plus eta 4 E2 d multiplied, the whole thing now multiplied by delta x. So you have to find the common multiplier for both of these. And once you do that, then you can go ahead and add. So once you do the addition and everything, and the equation that you will get will be of the form P2 sigma double dot plus P1 sigma dot plus P naught equal to, let's say, Q3 epsilon, there will be a triple dot plus Q2 epsilon double dot plus Q1 epsilon. So here P2 will be eta 1 plus eta 2 into eta 3 plus eta 4. P1 bit will be eta 1 plus eta 2 multiplied by E2, the whole thing multiplied by E2, plus eta 3 plus eta 4 multiplied by E1. And P naught will be E1 into E2. So I've given you one side, you can see the other side as well. If this is not very clear, you can we'll get Sarath to post this on the web also, and you can take a look.
Yes, sir, that would be more.
Okay, great. Do you have any other questions?
Sir, formation like this means if it is asked for instead of dashboard, if we are asked for spring.
Sorry, can you repeat it? I didn't really get you.
So like here it is given for Jeffreys model. So here eta 2 and eta 4 is given. Instead of that, we are given K1 and K2.
Then you have to repeat the same process exactly. I mean, all that will change is the constitutive equations, but the overall model will remain the same. So if they are in parallel, then they must have the same displacement, and then the forces will be additive.
Yes.
So the only thing you have to be careful about is how to write the constitutive equation. The two elements which are given to you could be anything, and all you need to do is to be careful with writing the individual constitutive element. Yeah. And once you do the constitutive equation, all you have to do is find the common multiplier and add them, and basically you have to figure out how to add them. So your whole task is this. See, if you ask two Jeffreys fluids to be put in parallel, your net force F is F1 plus F2. Now you want a relationship between F and delta X. But right now, when you write the constitutive equation, you get a relationship between F1 and delta X and F2 and delta X. You want to make sure you have a situation where you can add F1 and F2 together to make it F.
Yes.
And then immediately on the other side, you already have delta X. You don't have to worry about it. So then that will give you the constitutive relationship. So all your task is to figure out how to add the thing that you wish to add. So in this case, if they are in parallel, I'm sorry for all this noise. If they are in parallel, then the forces need to be added up. And that's what you are seeing. Yeah. And in series, it will be the other way around, right? So.
Sir, in one of the lecture, you explain simple shear flow and shear free flow.
Right.
So, sir, I'm little bit confused between both of them. I'm unable to differentiate what is the difference between both of them. Can you please explain
Simple shear and shear free.
Yes, sir.
Right. So simple shear is basically, if you think of a Couette cell, then you have one directional motion which is causing a shear flow. Okay. And the behavior of the flow type is exactly like that, where you have so if your shear flow is done where you want to subject the fluid only to shear, and uh, and the experimental situation can just be thought of as a Couette cell, or basically fluid between two parallel flat plates, where one of the plates is moving. Okay? So that is the shear, the simple shear flow. It's called simple because it's you basically are just causing it one component, right? And Pooja, I don't think I mentioned anything about shear free in this part because that was not the focus of. So I mentioned the simple shear with respect to trying to figure out the N1, N2, the normal stress differences in the fluid. So you want to impose that condition. That's how usually the normal shear, the normal uh, uh, stress differences, that's how they are evaluated, right? That you subject a fluid to a simple shear flow, and if it is purely Newtonian, you don't expect any all the components along the diagonal of the fluid, they are just minus p minus p minus p. So the normal components are the same. Whereas in a simple shear flow, if it is a non-Newtonian fluid, you'll start seeing differences. So there will be uh, the normal stress differences that will arise. Right? So that's why the simple shear flow is a experimental condition to which a fluid can be subjected, and you can measure N1 and N2. Yeah, and this is usually, for example, this is done in a rheometer. So if you have access to a rheometer, you can measure this response on the rheometer.
Sir, in assignment 1, there was a very first question about Deborah number. We needed to calculate the relaxation.
Okay. What was the exact question? Because I
Yes.
do not recall the questions right away.
It was given a uniform flow with a velocity u infinity is equal to 10 meter per second is passed through an area of cylinder with radius r is equal to 15 mm and the spacing between the cylinder is 40 mm with Deborah number 0.1. What is the time of relaxation of the fluid?
Okay, it's just 1 second. Okay, Pooja, so I have a question in front of me. Here, see, one of the length scales will be, so the length is given as L, but the fluid is passing through the middle of this two pillars, right? So this is almost like you can think of it as pillars, a cylinders, array of cylinders where it is passing. So your the length scale through which the fluid is passing is L minus 2R. And then the u is given to you, so you can find out the time scale of the flow. Deborah number is given to you, so you can now find what lambda is, and I believe the correct answer is 0.1. Is submitted 0.1 millisecond. So one quick other thing about this problem, there could be multiple Deborah numbers here. Okay, depending on how you want to calculate uh, the the time scale of the flow. But among the options given, the only one which will be the last one. Pooja, we answered your question, right? Pooja,
Yes, sir.
you got the answer, right?
Yes, sir. Yes, sir.
Okay.
So similar to that in assignment 2,
Assignment 2.
Yes. Question number 3.
Assignment 2, question 3. Okay.
Heaviside function related question was there. And we need to use the MATLAB software. But I didn't know that where to start this question. I even asked on the forum question that how we can start this. In the
Okay. So this. One second. Okay, in this question, there is one typographical error. The question was the stress history of the material. So the options is unfortunately on the y-axis it says epsilon t. It should have said sigma t. Okay. So sorry about that. If you got some marks docked for that, you just let us know. We'll see what can be done. But the whole point is that here the response is, so see, this is essentially related to the question of the step strain problem. So step strain has a solution, has a stress that you already know about because we talked about it in the class. But here it's not a simple constant strain that is provided. So the strain itself is changing from time. And this strain can be mathematically expressed as this minus ht, where h is a Heaviside function. Heaviside function is defined as being equal to 0. So h of t is 0 if t is less than 0. And then h of t is equal to 1 for all t is greater than 0. Okay. So that's how the Heaviside function is defined. It's also called the unit step function. You can look it up. So in some of the softwares, it's usually defined as the Heaviside function. Somewhere it is defined as a unit step function. And you need not use any particular any software in particular. But if you have access to MATLAB, I believe Heaviside function is already programmed in there. So now what you have to do is you have to figure out what the stress for this given epsilon t situation will be. Okay. And again, as I said, there's a mistake in the options. The y-axis should say sigma t instead of epsilon t. So basically, all these. So you already know the response for a single Heaviside function because that's what already in the class it's already been or in the course material it's already there, right? So now you have to basically add up the response. The stress will be the addition of all the individual responses to the Heaviside functions. So that's what you need to add up and figure out what the correct waveform is. So it's right. Yeah, I believe in one of the lectures, this early lectures, this problem has already been discussed. Something very similar has already been discussed, and even the code was given. No problem. Pooja, does that clarify your questions?
I think the code was not given. He has to explain this concept. But
Okay, so maybe the code was not given, but the question has been discussed already.
yes, sir.
Right. think we see Vishal here also. Uh, Vishal, the question forum is open. So if you have any questions, you can go ahead and ask.
is there any particular standard to means experimentally to measure the stress relaxation and creep in a rubber?
Experimental standard to measure
Stress relaxation.
stress relaxation and the other one is
Creep.
creep.
Yeah.
Um, no, unfortunately, I'm not aware of a particular standard in this case. Usually, what you would want to do is impose a stress such that the strains are small. So usually that's the only one that I'm aware of. I don't think I'm aware of any particular standard as such. Like believe what you're asking is equivalent of ASTM standards or something like that,
Yes.
right? I don't think so. Yeah. I don't think there are any standards. There might be some. Usually, when they do it, they usually try to do it for small displacements, small strains. But I don't have a number at the top of my head for that. Yeah, so I am not aware of any standard. I can look it up, and if I find something, I'll maybe have it sent your way. Okay. And something like creep also happens for metals. So if you keep a force for a very long time, metal will also tend to creep. So depending on the particular material, you'll probably have to look into the literature for that kind of material and see what is it that people tend to use.
Sir, if no more question, we can close. Sir.
Okay, thanks. So Pooja, if you don't have any other questions, then we can close. I don't think Pooja has any other questions.
Okay, sir.
Okay,
We can
okay.
close. Thanks.
Okay, thank you.